Hey everyone, Ron here from IKN. So today in this video we're going to talk about multi-joint movement coordination with particular focus on force estimation capacities. And what that is highlighting how the individual estimates how much force is necessary to complete a particular task. So every time we voluntarily reach towards a target of interest, our nervous system has to estimate the appropriate amount of force necessary to complete that task, which becomes very, very challenging when that force needs to be distributed across multiple segments and across multiple muscles that can carry out the same or similar function. So this will be described within the context of overshooting and undershooting. Okay, so anytime the nervous system, like I said, has to voluntarily produce movement or generate movement, it needs to estimate that force, and that force signal or that motor signal is sent along an alpha path or an alpha nerve, you can say, just to keep it simple. But that signal, that initial signal, is never 100% precise or accurate, okay, because we're typically moving in a complex environment and we're moving multiple segments at the same time. So what we need to have is a compensating system, and that compensating system is a gamma nerve, or the gamma loop, just to keep it simple again. And what that gamma loop does, or that gamma nerve does, is it helps to compensate errors in force estimation. But it can only compensate in a manner where the initial signal or the initial estimate is just below the necessary level of force. So for example, if I was to take the skeleton's hand here, let's say I was asked the skeleton to reach and touch my finger with its index finger. So before the skeleton moves, it needs to be able to estimate how much force is necessary to reach out and touch my finger at this particular distance. And that level of force will change relative to where my finger is, or relative to the hand. So if the skeleton estimates the level of force necessary, and then they reach, but then they move past my finger, they've overshot, or they've expressed more of an overshooting strategy where they've estimated that they've overestimated the amount of force necessary. Okay, now this makes it very, very difficult for that gamma loop to reflexively correct that movement error, that initial movement error, for example, because the gamma path can only excite. So it's much, much better to undershoot, to slightly undershoot the amount of force you need to estimate. So for example, if I was to reach, or the skeleton was reaching to my finger and it undershot, then the gamma nerve can register that change in muscle length that we haven't achieved the actual target of interest, and it can reflexively excite or increase force production to then achieve the target. Okay, but if we overshoot, then we just have to consciously reorganize the movement segments to change how they move to complete the task, or to reach the target of interest. So it actually takes much more energy to correct a movement error when we overshoot, for example, relative to undershooting. Okay, that's really, really important, because again, for the gamma nerve to be able to compensate for that undershooting, it can correct in the same direction. So we don't have to move in the opposite direction when we overshoot, but we can correct in the same direction, which actually allows for much less energy expenditure from a movement coordination standpoint. And that's why one of the key things that we focus on within our IKN Level 1 course is generating force estimation qualities, because this is something you see a lot in clients experiencing persistent pain, is an inability to express appropriate levels of force to complete tasks, okay, or to complete multi-joint movement strategies within a complex environment. We typically overshoot, we overestimate how much force is necessary. And what that does is it biases our movement control to more of a top-down control strategy, where the nervous system is trying to micromanage things. Because when we're overshooting, it's typically we're expressing too much muscle activity, which is a top-down strategy. But if we just undershoot, or if we produce just enough force, or just short of the necessary level of force that we need to complete the task, then we can allow for the reflexive systems, the preflexive systems, to compensate, which expresses a much lower energy expenditure strategy. Okay, now this is really important in a real world environment, because most of the movement in the real world is not going to be accurate. It's not going to be very precise. The signals that we send to the anatomy is not going to be very precise. We need to coordinate muscle activity. And so the capacity to estimate the necessary levels of force when we're moving multiple joint segments simultaneously is extremely important. And this is why you often see a lot of shaking occurring during some of the isometric strategies, the distal, the proximal isometric strategies that we use, because now you're adding in an extra segment or you're adding in extra tissues to the isometric. And when you do that, it makes it difficult for the nervous system to estimate how much force is necessary to maintain that position. And so you can see this fluctuation in muscle length changes because there's not an appropriate amount of alpha signal where the force or the motor signal, the initial estimate, is sent along, which means that the gamma system has to constantly compensate. So you see this constant fluctuation in muscle activity, which you observe as shaking within the limb. But that's actually challenging that alpha-gamma coordination, which is an extremely important process or phenomenon to challenge when it comes to real-world human movement. So important concepts to consider there. We need to challenge the capacity of the nervous system to estimate appropriate levels of force, but we don't want to overshoot. We want to work towards restoring necessary undershooting strategies, not too much below the level of force necessary, but just below, because that allows for the reflexive and preflex systems to compensate, which gives our system more options to manage multiple movement problems, because the environment's always throwing movement problems and chaos at the system, and we need to have an appropriate bandwidth or range of movement solutions to manage those forces. We can't necessarily do that if we're always overshooting and always overestimating how much force is necessary, because it leads to too much of a conscious focus or a conscious top-down focus strategy to control movement. By undershooting just below the level of force needed, it allows for a distribution of workload across the system by challenging those subconscious control mechanisms.